The textbook has listed a number of devices and situations in which fluid flows at a constant height and can be analyzed with Bernoulli's principle. I will mention a few here, and you can read the rest of them by yourself. According to Bernoulli's principle, pressure can be reduced in high-velocity fluids. In the case of this perfume bottle, the squeeze valve creates a jet of air, which reduces the pressure near the bottle mouth, and drops of perfume are sucked out and move with the jet of air. The Bernoulli's principle also helps to explain lift generated by a wing. The airplane wing has a characteristic shape as shown in the figure. The wing is tilted upward at a small angle, and the upper surface is longer, causing air to flow faster over it. The pressure on top of the wing is therefore reduced, creating a net upward force or lift. Sails also have the characteristic shape of a wing. The pressure on the front side of the sail, P-front, is lower than the pressure on the back of the sail, P-back. This results in a forward force and even allows you to sail into the wind. In other cases, such as water gushing from a large tube through a dam shown in this picture, we need to consider the effect of changing height. Actually, if resistance is negligible, the speed of the water coming out is just what it would be if the water fell a distance h from the surface of the reservoir. That is to say, the water speed is independent of the size of the opening. According to Bernoulli's equation, since both P1 and P2 equal atmospheric pressure, we can simplify this equation and solve for V2. We may notice that this is simply a kinematic equation for any object falling a distance h with negligible resistance, and this result is independent of the velocity's direction. Let's look at this more general example together. In this example, since the height is not a constant, we need to use Bernoulli's equation to solve for the pressure. According to Bernoulli's equation, we have this expression when comparing the initial condition at ground level and the final condition inside the nozzle. At the ground level, the pressure is 1.623 times 10 to the 6 Newton per square meter. The velocity of the water, V1, equals to the flow over a cross-section area A, and we get 12.4 meters per second, and the height is set to 0. Inside the nozzle, the flow Q is the same because the water is incompressible. We have the velocity of water, V2, equals the flow over the nozzle's cross-section area A prime, and we get 56.6 meters per second. The height of the nozzle is 10.0 meters. So we rearrange this equation and get P2 equals to P1 plus this whole thing, and we get P2 around 100 Pascal. Please note that this P2 is the gauge pressure because P1 was a gauge pressure. This means that the absolute pressure in the nozzle is very close to the atmospheric pressure, which makes sense because the water exists into atmosphere without changes in its conditions. Since in Bernoulli's equation, this constant has a unit of energy per unit volume, we can multiply it by flow rate, Q, which has the unit of volume per unit time, and then we can get a unit of power. You can see that each of these three terms has a clear physical meaning. The PQ is the power supplied to a fluid, perhaps by a pump, to give its pressure P. The half rho v squared times Q is the power supplied to a fluid to give it its kinetic energy. And rho gh times Q, the third term, is the power supplied to a fluid to give its gravitational potential energy. We have been ignoring any friction in the fluid flow, but if we do consider real fluid and include the friction, or more accurately, the factor of viscosity, we can see there are mainly two types of flow: the laminar flow and the turbulent flow. Laminar flow is characterized by the smooth flow of fluid in layers without mixing, while turbulent flow, or turbulence, is characterized by eddies and swirls that mix layers of fluid together. There is generally more interaction, greater heating, and more resistance in turbulent flow than in laminar flow. Sometimes we can predict if flow will be laminar or turbulent. We know that flow in a very smooth tube or around a smooth, streamlined object will be laminar at no velocity. We also know that at high velocity, even flow in a smooth tube or around a smooth object will experience turbulence. However, at intermediate velocities, flow may oscillate back and forth indefinitely between laminar and turbulent. For example, flow is laminar in this large part of the blood vessel and turbulent in the part narrowed, where velocity is high. However, in the transition region, the flow can oscillate between laminar and turbulent flow. The fluid friction, both within the fluid itself and between the fluid and its surroundings, is called fluid viscosity. The precise definition of viscosity is based on laminar or long turbulent flow. This figure shows how viscosity is measured for a fluid. Two parallel plates have the specific fluid between them. The bottom plate is held fixed, while the top plate is moved to the right, dragging fluid with it. Care is taken to ensure that the flow is laminar, and it is found that the force F required to keep the top plate moving at a constant velocity v depends on four factors: the velocity v, the area of the plate A, the distance between the plate L, and the coefficient of viscosity, eta. So that we have the fluid viscosity, eta, equals to FL over VA. Viscosity varies from one fluid to another by several orders of magnitude. The viscosities of gases are much less than those of liquids, and these viscosities are often temperature dependent. Since we will be only considering ideal fluids with little or no viscosities in our calculation, we will stop here and you may read further contents of the textbook if you are interested. When we consider the fluid motion in the level of molecules, we have another mode of fluid motion called diffusion. Diffusion is the movement of substances due to random thermomolecular motion. It can be shown that the average distance x RMS that the molecule travels is proportional to the square root of time, where x RMS stands for the root mean square distance and is the statistical average of the process. The quantity d is the diffusion constant for the particular molecule in a specific medium. Diffusion naturally proceeds from a region of higher concentration to a lower concentration. The net rate of movement is proportional to the difference in concentration. Let's look at this example together. Since we know that the molecules moves 1.0 centimeter, which is 0.01 meter, we can rearrange the equation and get the time it takes equals to x RMS square over 2d, which is the 0.01 meter square over 2 times the d given here, and we get 21 hours. So it takes 21 hours for one molecule to move 1.0 centimeter in water.